So thanks for coming. I have the pleasure today to introduce our speaker for the special energy seminar. Today is the deadline for the PISM proposals, so hopefully a few more people will join. You can still grab some ideas to hone your proposal from the final touch-up. So our speaker of today is Yen-Ting Lin. He's a research fellow at the Institute of Astronomy and Astrophysics, Academia Sinica in Taipei, Taiwan. He's currently a sabbatical visitor at the Institute for Advanced Study in Princeton. He works on various aspects of galaxy formation and evolution, including the assembly history of brightest cluster galaxies, detection of distant galaxy clusters, the initial mass function, triggering and quenching of star formation. He's a member of the Subaru Hyper Supreme Chem and Prime Focus Spectrograph surveys, as well as the Rubin Observatory Legacy surveys for space and time. He's visiting us until tomorrow.
I will also give a talk at Lars' group meeting on BCG formation.
Okay, good. Oh, sorry. So you can schedule your appointment with him on our usual spreadsheet for today, late today and tomorrow as well. And today is going to talk us about some progress on Galaxy Halo connection. Take it away.
Yeah, thank you very much. I'd like to thank Bill, Dee, and Federico to make this happen. And that allows me to share with you some of our recent works on Galaxy Halo connection. I would like to highlight the contributions of my former and current students shown in the first row here, and the rest are my great collaborators for the projects I'm going to talk about today. Well, sometimes I think this always happens. It'll froze. So Galaxy Halo connection tries to cover is a vast topic, trying to answer a seemingly simple question, namely, how do galaxies populate dark matter halos? How do we go from this, an embodied simulation, to this, the observed galaxy distribution? So in this review by Wexler and Tinker, they listed 5 different approaches to model galaxy halo connection, from hydro sims to semi-analytic models to empirical models such as universe machine emerge or deep sky, to subhalo abundance matching, and then finally halo accumulation distribution or HOD. As HOD will play some roles in the projects that I'm going to talk about, I will describe this in some more details. But before that, let me introduce 2 sets of concepts, namely the distinction between central and satellite galaxies, as well as the distinction between halos and subhalos. So we know dark matter halos, as shown here, has a lot of substructures. So if you take out kind of self-bounded structures, which are called subhalos, then you are left with one body of halo, and we call this the main subhalo or central subhalo, and these are the satellite subhalos. This is because structure formation proceeds in a hierarchical fashion in CDN, and so when a halo falls into a bigger halo, the central part of that halo, because it's dense, it can remain its identity for a long while. So it becomes a subhalo of the resulting bigger halo. And then on the left, I have this simple cartoon showing some galaxies living in halos. So each star is a galaxy, and then the blue circles represent halos. So if there's only one galaxy in a halo, we call it the central galaxy. for halos that host more than one galaxy, we usually refer to the one that lives closest to the bottom of the potential well and the most massive one as a central galaxy. And then call the rest of the galaxies satellites. So these are the two simple concepts that I want to introduce. And that will be useful in the HOD formalism, which is basically just pair counting. So we already see these three halos. So given the occupation number, which is basically the number of galaxies in a halo as a function of halo mass, which is shown here. And then the halo mass function, the bias mass relation, the linear Paul spectrum, and the way galaxies are distributed within the halo, we can use the equations here to derive the HOD. And you can think of this as composed by one halo term, which is the pairs within galaxies living inside a single halo, as well as the two halo terms. This is the pair counting between galaxies living in different halos. So this is the way you calculate the one halo term and the two halo term. This will give you the resulting Paul spectrum. And then by combining of those one and two halo terms, you can compute the Paul spectrum or its Fourier transform, which is the correlation function. And then this is the correlation function shown as the line curve. And then we can compare with the data so that we can adjust the parameters here, such as how galaxies are distributed in a halo, whether they follow an NFW profile. If so, what's the concentration? Is it the same as the dark matter halo or different? Or trying to adjust the shape of the occupation number, then when we find a good match with the observed correlation function or Paul spectrum, then we can understand how galaxies populate the halos, right? Because we now know as a function of halo mass, how many galaxies there should be, and how are these galaxies are located within the halos. And then we can try to understand why galaxies populate halos this way. So this is pretty much how we will try to understand galaxy formation in the framework of galaxy halo connection. Okay, so this review was written back in 2018, and since then there are many new developments. So one omission was constraint simulations. So these are simulations that have a special initial condition, so that by evolving to certain redshifts, maybe 2 or redshift 0, they will be able to reproduce certain observed large-scale structure. And the other is machine learning. So nowadays this is super popular. So and people have been using machine learning to enable more efficient or more insightful ways to study galaxy formation. And today I'm going to touch upon constraint simulations, HOD, and machine learning. First, I will use a constraint simulation to help me detect or characterize the halo assembly bias at galaxy cluster scales. And then I will introduce a formalism that's basically an extension of the HOD to estimate the halo mass and its probability distribution function, PDF, by purely counting the number of neighboring galaxies from a given galaxy. And I will end with a GNN model for predicting critical baryonic properties such as star formation rate, stellar mass, color, and other properties purely from dark matter merger trees. And that's accurate from version 0 to 5. Okay, so let's start with assembly bias. We know dark matter halos are bias tracers of the underlying matter field in the sense that more massive halos are more biased. And now we also know that bias doesn't just depend on halo mass, but also depend on other halo properties such as the formation time or concentration, or even the spin of the halos. So these effects are collectively known as assembly bias. So from this plot by Jing et al., he was looking at the bias of the youngest and oldest halos. So the blue are the youngest and the red are the oldest halos. So you can see that for low mass halos with mass about 10 to 12 solar masses or so around here, the earlier forming halos will have about 40% larger bias. So the bias difference is very apparent. But then if you go to cluster scale halos, like 5 times 10 to 14 or so, you see that actually the blue points are higher than the red points. Namely, the younger clusters or younger halos actually have higher bias than their older counterparts with the same mass. And actually, the degree of this depends on the formation plan definition, but we're not going to delve into that today. And since assembly bias is a robust feature of lambda CDM, I believe it's important to find observational evidence for that. And also, the existence of assembly bias is kind of a threat to HOD models because in HOD, the basic assumption is that halo mass is the key, the only parameter that controls galaxy formation. So if assembly bias exists, that means there are other things that will affect halo formation and presumably galaxy formation. So that will kind of undermine the basic assumption of HOD. So I have tried to detect assembly bias for almost 10 years now. And one lesson that I learned from all the hard work was that it's critical to have a reliable proxy of the halo formation time that works on individual halo basis. So basically, if you are able to label or have some information about the formation time for individual clusters, that will be dream come true. Unfortunately, we are not there yet, and I'm not sure if we will ever be able to do that. But today I'm going to present a method that allows us to approximately do that. So using the group catalog of Yang et al., Wang et al. Have run a constraint simulation of the local universe called Elucid. So starting from the galaxy distribution, this is from Sloan DR7. This is galaxy distribution projected on a plane. And then they constructed a galaxy group catalog. After correcting for the redshift space distortion, they were able to construct the Sloan density field out to redshift 0.12. And then with a clever way of rapidly exploring the initial conditions, they came up with one that will evolve into the density field that looks just like the Sloan. So basically, in this elusive simulation, for structures larger than 2 megaparsecs, which is the typical size of a massive cluster, there's a very good correspondence between the Sloan large-scale structure and the elusive large-scale structure. So we took this advantage of this high fidelity simulation of the local universe and selected the most massive 600 clusters at redshift less than 0.12 from Young's cluster catalog, and then try to match those clusters to the halos in the elusive simulation. And we actually find a very good correspondence. So we then take the simulated halos for which we know their formation history, and then we are able to label the clusters as young and old. So this allowed us to have a 138 oldest clusters and 121 youngest clusters. Here, the clusters are labeled by Z20, which is the redshift when the halo has assembled 20% of its final mass. And so we basically took the extrema in Z20 and limit our cluster mass within a certain range. And so is the redshift. So this is the selection halo mass. That's from Young's halo mass. And then the clusters lie in this redshift range from 0.06 to 0.12. Then we stack all these clusters using Sloan shear catalog. This is our shear measurements. So you see there's some difference between the young and old clusters, but their masses are within 1 sigma. So for our late forming cluster sample, the mean mass is 1.3 times 10 to the 10^14, while that for the late forming sample is 10 to the 14, so within 1 sigma. And then in this panel, I'm showing the relative bias of the early and late forming halos or clusters. So they are represented by the red and blue symbols. And then taking the ratio of them, which is shown as the solid green symbols in this panel, you see they are far from unity. In other words, the early forming halos have much lower bias compared to the late forming halos. This is consistent with the prediction of CDN. So we have a strong detection of assembly bias. And the theoretical predictions are shown as open triangles. So you see that our measurements are very close to the predictions. And so we further look into the galaxy properties in these clusters, trying to see if they are indeed consistent with this cluster samples being young and old. So we measure the spatial distribution, projected spatial distribution of galaxies in the early forming and late forming samples. The black, red, and blue symbols represent all the galaxies, red and blue galaxies respectively. And if you fit an NFW profile to the red galaxy distribution, you'll find that the concentration for the early forming sample red galaxies is 7.1, while that for the late forming sample is 5.6. Although the error bars are large, but this is consistent with the notion that these clusters are older, and so the galaxy distribution, if they follow that of the dark matter halos, should also be higher compared to that of the late forming sample. We also integrated the number of galaxies and found that the galaxies in our early forming sample is only 75% of that in the late forming sample. But recall that there's some difference in the in their masses. So the early forming sample is actually slightly more massive. And then we know that the number of galaxies in a cluster goes as cluster mass to the 0.8 power. So combining all this together, this shows that there's a 60% fewer galaxies in the early forming clusters than the late forming sample if there's no assembly bias. So you have to have assembly bias to explain such a deficit in the galaxy number. We look at the differences in the mean age of the brightest cluster galaxy, BCGs, and other member galaxies, but we didn't detect any difference in their age, which probably is due to the fact that beyond certain ages, you simply cannot tell which are older. But we do see some evidence of difference between the magnitude gap between the BCG and the second most massive or luminous galaxy. So in the early forming sample, the magnitude gap is 0.44. On that, in the late forming sample is 0.38. So this is a significant difference. And there's also difference in the offset between BCG from the cluster center. So here the cluster center is defined to be the geometric mean of the member galaxies. And so for early forming sample, it's 11% of R200, which is slightly smaller than that of the BCGs in the late forming sample, 14% of R200. So all of these are consistent with the notion that our early forming samples is indeed older, allowing BCGs to sink or settle to the bottom of the potential well, and then accrete or eat with whatever galaxy that sinks to the bottom of the potential well due to dynamical friction. So as a sanity check, we also constructed 14 pairs of randomly selected cluster samples that have the similar distributions in halo mass and redshift as our real sample. So these 14 pairs are shown in these 14 panels. So the three numbers are the masses, main masses of the early and late forming samples. And the third number is the probability for the relative bias to be consistent with the theoretical predictions, which are shown as the horizontal dashed lines. So you can see that the probabilities are all very high. And none of them are as low as the real measurements. And also, for the BCG offset and magnitude gap, for these random samples, they are basically the same. So that's another proof that our real sample is really special, showing that showing a strong signal of assembly bias. So any questions so far? Okay. So we believe we are among the first group to show a firm detection of halo assembly bias at the cluster scales anyway. So that's an important validation of lambda CDN. But as you know, this is kind of informed by this constraint simulation. So it will be very important to find ways that are more directly linked to the observations, so that we can label clusters as early forming and late forming. So we hope to use the observables that we found, like the galaxy spatial distribution, the galaxy number, the BCG offset from the cluster center, and the magnitude gap, so that we can purely construct cluster samples, early and late forming samples from observables. And I just want to mention that this for modeling techniques that can reconstruct the density fields, like elusive, has become popular. So there are many different methods in the market, and that will be very helpful for surveys like DESI and PFS, prime focus spectrograph. And that will allow us to do the reconstructions at high Z and study assembly bias and other properties in the early universe. So please look at this paper for more details about this approach. Then, this is related to the study of assembly bias. So in addition to being able to know the age of a halo, you also need to know the mass of a halo, right? So I'm going to present a new method to estimate the halo mass of any galaxy. So traditionally, we will rely on expensive observations like X-rays or SZ to detect, to measure or estimate the halo mass for a cluster or sometimes even a massive galaxy or group. But for less expensive methods, we typically have to rely on stacking technique. So that will only give us the mass in a statistical way, such as lensing or satellite kinematics. So I want to argue that actually with a spectroscopic survey like Sloan or DESI, we already have enough information to estimate the post-halo mass for any galaxy in this surveys. So I already showed you a halo occupation number, and then from this, we can construct the HOD will allow us to predict this probability, the number of neighbors within certain apertures, given a halo mass. So this RP is an aperture. It can be like 0.3 megaparsecs or 1 or 1.2, 1.5, whatever megaparsecs. For a galaxy living in a halo with mass m, and we have one halo turn and two halo turn. The one halo turn consists of the central galaxy as well as the contribution in the from satellite galaxies. Oh, okay. So given the time, I will not go into details, but I also want to say that with two halo turns, we also have contributions from the mean number of background and also correlated structures, which is coming from the correlation function of galaxies. We know galaxies are not randomly distributed in space. So with this formalism, we're able to predict this NP as a function of the aperture. So the three curves are for galaxies living in three different halo mass ranges, 10 to 12, 10 to 13, 10 to 14. So the curves are our model predictions and crosses are the results from mock, basically the truth. So they are quite, I think, in reasonable agreement. We can then use the Bayes theorem to invert that, to infer the mass PDF, even the number of neighbors we measure. And so, for example, this is the PDF as a function of halo mass. So if you measure 30 galaxies within a 0.5 megaparsec aperture, this is the curve. The red curve is the PDF it will give you. You can compare that to the crosses. They are, I think, in reasonable agreement. If you only measure 3 galaxies, on the other hand, you are most likely to be in a low mass halo, but you can also have some probability to be in a more massive halo. Maybe you are at the outskirts of such a more massive halo. So I'll skip the formalism, and just to show you that it should work. And I'm showing you the preliminary results here. So we took the HOV from the Sloan DR7 measurements. Specifically, we used this R magnitude brighter than -21 subsample, which is this the black curve. And I think it's this halo occupation number. So we plug in this the HOD parameters to our formalism, and then we combine the neighboring count PDF from the neighboring counts between 0.3 and 1.5 megaparsecs. And these are our mass measurements from the PDF method compared to a lensing mass. This is 1-to-1 relation. So it's kind of reassuring that they are not way off. Remember, because we only use the public HSC shear catalog, we only have 220 and 20 galaxies, 220 and 20 galaxies in these three samples. So that's why the error bars on the PDF mass is large. If you just take the young group catalog and measure their lensing mass, you see that it's highly biased. So that's why I believe our method is more robust. And this shows the PDF of the three mass ranges. So because of the small number of galaxies, we are not able to really select galaxies with a PDF single peak PDF. So if we can use the whole HSC shear catalog, then we should be able to be more picky and select galaxies with more cleaning looking PDFs, and that will shrink the error bars and hopefully put them in the 1-to-1 relation. And this way, we can really estimate the PDF of a given galaxy in this sample. Okay, so I guess I'm running out of time, right?
2 minutes.
Okay, so in 2 minutes, I can show you this last part. So basically, we have an emulator that's based on a GNN model. And so from at the beginning, I'm asking the question, how do we go from this to this? And with this model, we can go from this to this. So basically, if we can construct a good mock galaxy catalog that resembles the observed sky, this one, then we should be able to work out what's the underlying cosmology. So, as I said, we train us, well, I didn't say that. So we trained our model based on TNG 300 simulation. We split the box into 8 pieces and use 6 of them to train our model. And then 1 piece for validation and 1 piece for test. And for the 6 boxes, 6 of these boxes, we compare the hydro run and the dark matter only run, and then trained the model so that it knows the number of mergers and the properties of dark matter halos and subhalos in subsequent snapshots, so that purely from the merger trees, we can predict stellar mass, gas mass, star formation rate, color, stellar and gas metallicity, all the way to redshift 5. And so this just shows the true and predicted stellar mass, star formation rate, and color. You can see that they are unbiased. And then this shows the stellar mass growth history for 2 stellar mass bins chosen at the present day, the more massive bin and the less massive bin. And you can see the mean and the predictions are overlapping all the way to redshift 5. This shows the zooming. You can see that our masses are unbiased. So I believe this is a good way to port whatever hydro model to a bigger box with the same resolution, right? TNG can only afford to run 300 megaparsecs because it's very expensive. But with this model, it learns the physics of TNG. Then we can use an embodied much bigger box with the same resolution as TNG, and then just populate this box with the TNG physics-based galaxies. And of course, one caveat is that TNG should be a good model of the universe. But in terms of clustering, unfortunately, at redshift 0.5 or 1, they don't really separate the blue and red galaxies well. As shown, I mean, we observed that in the observed correlation function. You see the red and blue galaxies are really separated in their correlation function, but that's not what we found in TNG. So anyway, if you have a good model and before running a bigger box, it's good to try our model first and see whether the galaxy properties at much larger scales matches with that of the real universe before starting to run a bigger simulation. And so I'll just leave my summary here and thank you very much for your attention.